Well, thank you all, and thank you for inviting me to the conference. Today, like Stan said, I will be talking about a learning-based approach to inverse problems with forward models, and we'll likely start with a learning-based approach for inverse problems with known forward models. The goal of this work is to combine two developments. First, thanks to hundreds of years of physics research, we now have very accurate models for how light and waves propagate. And in the last decade, we have these amazing deep learning-based priors for what natural images look like. I could use the DALL-E 2 generation engine to create a new lab logo for my lab. And the goal of this research is to combine these physics-informed forward models with off-the-shelf deep generative models to solve computational imaging and sensing problems with unknown and/or stochastic forward models. Now, before getting to that, let's recall how do we apply deep learning to imaging? How do we apply deep learning to computational imaging problems, where our goal is to recover a signal, recover a image X from measurements Y that have some known forward model A, where that encodes our prior knowledge about the physical process. That's how the signal of interest gets mapped to our measurements that we have. This is a very general framework, and for the purpose of this audience, we can think of it as Fourier phase retrieval. We have some complex field X, we have the 2D Fourier transform operator, and we capture noisy intensity measurements. And there's three sort of prototypical ways to approach this problem with deep learning. We could simply train a network to learn a mapping from measurements back to signals. Alternatively, we could apply a plug-and-play algorithm that uses sort of a pre-trained denoising algorithm as to iteratively impose a prior on the reconstruction. And alternatively, we could restrict X to the range of a deep generative model. So by far the most straightforward of these approaches is just learning the mapping from Y to X. George did this back in 2017, and others have done it in simulation even before that. But here the goal is to train a network just to map from measurements, map to signals. And to do this, we start with a set of training data. We assume we have a large representative set of training data. This could be MNIST, this could be all natural images, this could be all MRIs, what have you. And this resides in the signal space, and consists of a very small manifold, a very small set in that space. The vast majority of images are not natural images. And then with this set, with this set of training data, we can then feed it through our forward model, through our physics-based forward model, get a set of simulated measurements. Now we have paired data, and can train a network to go from Y to X. And alternatively, you could actually do this at sort of extreme cost by just capturing lots of experimental data. This can be applied successfully to a range of problems, including phase retrieval. Back in 2020, we applied it to non-line of sight imaging with speckle correlations, where we're solving a very, very low light, phase retrieval problem, to the point where you don't have enough light to reconstruct things with classical techniques, and machine learning, using simple learned priors, can let you operate, in near real time to image around a corner. So here we have light, that bounces off a wall, illuminates some hidden scene, bounces off a wall again, and is imaged by a camera. We take some speckle patterns, compute the autocorrelation, and reconstruct the signal from the autocorrelation. Now the sort of major downside with this approach is that it's essentially the network you train is trained for a particular mapping, for a particular forward model A. And so if the physics of the problem changes, if you recalibrate, what have you, the network you've learned now is essentially useless. It's mapping this set to this set, where what you really need now is a mapping from this set to this set. Now, an alternative approach that gives you the flexibility to handle these changing models is plug-and-play reconstruction. And the intuition you can have with plug-and-play is that you have the set of signals that are consistent with your measurements. So this is the set of Y equals AX. So if this is a linear operation, this is a matrix multiplication. This defines a linear subspace. And then we have the set of all natural images, natural MRIs, natural what have you. And we're interested in finding the intersection of that set. What is the signal in the set that is consistent with the measurements, which is to say, where does that set and that set intersect? And you could imagine you could have a simple projected gradient descent like algorithm where you project onto that set, project onto that set, project onto that set, yada yada yada. You can make this a little more formal by turning to maximum a posterior estimation. So let's give a map estimate of the signal x that it minimizes some objective function where we have the data fidelity term and the regularizer term, where ideally this is the negative log likelihood of of the data. For a given reconstruction x, how likely was it that I observed y, and r of x is the negative likelihood of the data distribution. From there, you can set up any number of algorithms, but perhaps the simplest is just proximal gradient descent. So let's take a gradient step to reduce f of x, then use a proximal mapping to reduce r of x. Note here that we're physical model is baked into this algorithm in the use in this step where it takes advantage of our knowledge of the forward model A. But then, looking at this, what should stand out is that, to minimize this term, we need the negative log likelihood of the data. So, what this is asking is, given an image, how likely is this that it's a natural image? Not an easy problem. And to, approach that problem, we can, in sort of the plug and play's key insight that made that problem tractable is that denoising, a really good denoising algorithm, whether it's a learning-based denoising algorithm or something classical like BM3D, has a lot of that knowledge baked into it already. So let's think about map estimation for denoising. So we have a signal x that we'd like to recover, where x is contaminated with additive white Gaussian noise. We know the log likelihood of the measurements, and the map estimate is just solving this this optimization problem. And if we have a really good denoiser, we can squint and assume that, hey, it's probably solving this. And you can make this a little more rigorous by, Tweedy's formula, where, essentially you can interpret a minimum mean square error denoiser as taking a gradient step up, up the sort of the blurred log likelihood of the data. But the key takeaway here is that if we have a really good denoiser, we implicitly know a lot about the data distribution. And so, with that understanding in hand, we can take our proximal gradient descent algorithm and, replace, what was a, proximal step with respect to the data's negative log likelihood with a denoiser. And this is sort of a, general framework that allows us to plug in, essentially arbitrary priors in the form of a denoiser to reconstruct the signal. And it can be easily applied to a range of problems, including compressive sensing, where total variation priors compared to plug and play with BM3D and deep neural networks on the right. Also can be applied to phase retrieval problems, including coherent, both with coherent diffraction patterns, and in the more challenging case of Fourier phase retrieval. Although in this case, the initialization becomes a little more tricky. Right. And so, then, so that's the plug and play approach. And then, the third approach, and the one that I'll, build on later on in the lecture, is restricting X to the range of a deep generative model. So, here, let's simply find an X that is consistent with our observations Y. And, we're using this least squares fit here, but, this could be, sort of arbitrary. It could be the negative log likelihood as well. And our prior on X is that we can represent it, in the range of a deep generative model. We have StyleGAN, we have some deep generative model that can, produce all these, very realistic, impressive-looking images. And we're going to find a, reconstruction X that is inside the range of D. And the image to, have in your mind here is that we have, some latent space of the deep generative model. Some low-dimensional latent space. Our deep generative model, our CNN, maps us to a set of signals, and we can use this, data fidelity term to, map, an observation here to a measurement here compute the least squares, backpropagate all the way into the latent space, and so maneuver within the range of the deep generative model. And this has been applied, so this was first proposed by Bohr et al. And Alex Demakis' group, and it's since been applied to a range of problems, including denoising, tomography, compressive sensing, and phase retrieval. And as we saw, Michael and George mention earlier, we can sort of tweak this framework, and this is what I'm describing as sort of a slight abuse. But we can think of, what if rather than restricting it to the range of the deep generative, a pre-trained deep generative model, we restrict it not quite to the range, but to a low-cost surface from an untrained generative model. Find a signal that can easily be fit by a untrained generative model. So this is the idea behind deep image prior and deep decoder, where these two have been applied successfully to a range of inverse problems, including by Laura Waller and others. So to summarize, if we know the forward model and the forward model is fixed, various deep learning methods give us a broad tool set with which we can apply and solve computational imaging problems to great success. The problem we're interested in this work is a little different. We're not interested in reconstructing Y from a known forward model. We're interested in reconstructing Y from an unknown forward model. So we have a parametric unknown forward model. So we have Y is equal to A theta I of X, where the latent parameters are unknown, and these latent parameters, specify the forward model. So A theta could denote convolution with an unknown blur kernel, tomographic projection with an unknown view angle, coherent illumination with an unknown source. We're interested in these sort of the blind forms of these problems. And taking a brief aside and sort of motivating this, one application where this shows up, where you might not expect it, is in non-line of sight imaging. So the basic idea behind non-line of sight imaging, which was first demonstrated back in 2012, is essentially we can use what's essentially a LiDAR system to image around a corner. So let's have a pulse laser source and a time of flight detector, and we're going to scan along locations on a wall, and at each location we're going to get isotropic scattering is going to interact and scatter off the hidden scene. Some of that light's going to make it back to the wall, and then we capture a histogram on our time resolved detector. And so for every location on the wall, we get a measurement that looks something like this, where we have time, which is the same as round trip distance on the x-axis, number of photons on the y-axis. And so it's essentially an unknown view. It's essentially a tomography problem. Not unlike ultrasound. And just like in standard tomography and imaging problems, the resolution you can achieve with this system is determined by the size of the aperture. So the larger the area on the wall you scan is, the higher the smaller the resolution the features you can resolve are. Now, this was originally motivated by the question, can we see inside a room with an open door, using a door? And the problem we sought to tackle is, can you see inside the room even if the door is closed? And so here we restrict ourselves to a single optical path. So we have essentially a LiDAR system on the outside, and we're going to illuminate along a single optical path into the hidden volume. Light's going to scatter, interact with the hidden object, come back to the wall, scatter again, and some very small fraction of the light's going to make it all the way back to the time resolved detector. And conventional wisdom says that should be the end of the story. That there's just not enough information from one time resolved measurement to reconstruct much of anything about the hidden scene. But if you assume the hidden scene's moving, then the story changes. And the key insight here is the key insight behind inverse synthetic aperture radar. Measurements of a moving rigid object captured with a fixed sensor are equivalent to measurements of a fixed object captured with a moving virtual sensor. So with some slight abusive notation, we have the forward model of a translated version of the scene with some scan location theta, is equal to this sort of a fixed version of the scene with a translated sensor. Now the forward model is given by this, where we have speed of light, time relative to the laser pulse, sort of Lambertian cosine terms. You can largely ignore that and just think of it like a spherical radon transform. So for every, for every point on the wall, you're capturing a spherical radon transform of the scene. If the scene moves, if the object moves around, you're effectively moving around, where the center of that spherical radon transform is occurring. Important takeaways are that this forward operator is linear, and it's parameterized by the position of the scan point relative to the center of the hidden object. And so from here, we can set up the following optimization problem, where we observe, a sequence of observations, each with different unknown latent parameters, where the latent parameters denote the location of the hidden object. And our goal is to use these measurements to reconstruct X. And this is just an unknown view tomography problem, for which we can then turn to the literature in single particle cryo-EM and set up expectation maximization or any number of Bayesian algorithms where we take a lower bound on the log of likelihood using Jensen's inequality. So essentially perform soft assignments of where we think the object is at each step, maximize the lower bound, reconstruct the object, and repeat. Get a better estimate of the object, get a better estimate of its location over and over again. We applied this to the following experimental setup. So we have light going through the keyhole, bouncing off the hidden object, back through the keyhole, and the object's on a translation stage, moving around. Again, any one of these observations, not a whole lot of information here, but if the object moves around and you capture a sequence of observations, the story changes. You get a sequence of histograms. So this is different time, so this is sort of slow time. This is fast time, this is distance. Plug this collection of measurements into expectation maximization and get back the following reconstruction of the object and its trajectory. And we applied this to a range of different objects, range of different trajectories, and got fairly low resolution, ghost-looking artifact with some ghosty-looking images. And also fairly accurate estimates of their trajectories as well, sort of for free from this algorithm. The next step here is how do this is all sort of classical optimization-based approach to this problem. How do we incorporate machine learning? Now we had the previous solutions. We could just train a network to learn a mapping from y to x, but in this case, it would require training over all possible latent parameters. So sort of quickly explodes the amount of training you'd have to do. These plug and play and restricting yourself to the range of a deep generative model, they're also challenging because you can't take a gradient step if you don't know the latent parameter. Now, potentially you could jointly estimate the signal and the latents, but this is prone to get stuck in local minima. And alternatively, you could marginalize over the latents. And in this particular problem, sort of that motivating example, this would likely be enough. There's x and y. There's not that many. The dimensions of the latent variable isn't very high. But as we'll see, this quickly becomes computationally intractable for other inverse problems with unknown forward models, where the latent parameter space is much, much, much higher dimensional. So in this work, we turn to an approach developed by Michael Unser's group, by Harshit Gupta et al. In their recent CryoGAN paper, where we are going to use an adversarial learning. So we're going to use a discriminator network, as I'll describe later on, to come up with a reconstruction X, which is not consistent with these Ys, but rather produces a set of predicted observations. So if we fed our reconstruction through the forward model many, many, many times, we'd produce a sequence of predicted observations that follows the same distribution as our actual observations. So the takeaway here is we're comparing distributions, not individual realizations of the measurements. And so the tool we take advantage of here is it's generative adversarial networks. So we have a generative network. We have a discriminator network. The generator is, its goal is to produce, realistic-looking, fakes, realistic-looking synthetic images. And the discriminator its goal is to, say, is that a real image? Is that a fake image? Essentially to fight the generator. And so, we have a sequence, a collection of images that we'd like to, replicate the distribution of these images. The generator, spits out an image at initialization. It's a pretty terrible image. The discriminator, easily compares these two, identifies, that's not a realistic looking image, provides a feedback signal to the generator, which then, gradually updates its reconstructions until eventually it's producing, reconstructions that, follow essentially the same distribution as the actual, training set. Fools the discriminator. And this framework has been applied successfully to generate a range of different images. We can use this framework to reconstruct, to generate bedrooms, generate ImageNet data, generate faces. And the key insight Harshit and others had was that, hey, we can also use this framework to generate measurements. Let's not use the generator to generate images, but the measurements those images would have produced. So here, the generator is looking to produce a collection of measurements that follow the same distribution as the actual measurements. And in their case, this was applied to cryo-EM, where you have these very, very noisy tomograms at unknown orientations. And using the framework I'll describe shortly, they eventually got the generator to produce noisy tomograms that followed the same distribution. And embedded in this generator framework is implicitly, is a reconstruction of the signal, a 3D reconstruction of the signal. And again, the takeaway here is that using this GAN framework, we can ensure that the distribution of our predicted observations match the distribution of the true observations. So the general adversarial sensing framework works as follows. We have the physical scene, has some unknown latent parameters. We capture a sequence of observations, and we have these observed measurements. So this is what you're given. And then we are going to have a generator network, and generators, a bit of a misnomer here, in that this is reconstructing just a single signal. So it's a bit like deep image pry or something. This is not producing lots of images. It's producing a single reconstruction, and you're training it, the single reconstruction, to be consistent with these observations. And you take your reconstruction, you pass it through a differential renderer. You pass it through your model of A, with various simulated latent parameters, so view angles, what have you. You get a simulated sequence of measurements. Initially these look like garbage, but then you have a discriminator which compares this distribution and this distribution, and provides a feedback signal that gradually gets these two to match. The benefits of adversarial sensing is that it produces, supports unknown forward models and unpaired measurements. As I mentioned previously, Michael Unser's group successfully applied this to solve the cryo-EM problem. My group has worked to reapply this framework to imaging through turbulence and sub-diffraction imaging with Fourier ptychography. The turbulence problem is essentially a really, really challenging blind deconvolution problem. So, turbulence is caused by inhomogeneities in the index of refraction of the atmosphere, due to expansion due to heat and what have you. And our goal is to take a sequence of images that look like this and reconstruct a nice crisp image. Now, Fourier optics 101, we can, at each point in the scene, the point spread function is, determined by the, essentially the phase error, at the aperture plane, that whatever phase is directly at the aperture. And, if we have no atmospheric turbulence, a point source is going to produce a plane wave when it hits the aperture. We get a, Fourier transform of this aperture, and we get a nice, Dirac-like point spread function. Not much, very little blur. If we introduce atmospheric turbulence, now we have a, identity phase error, and we're going to get, a distorted PSF. This is just, the model that describes each of the point spread functions. What makes this problem challenging is each pixel in the scene is subject to its own phase delay and its own point spread function. And so, we get a phase error like that up in this region, phase error that looks like that down in this region. And, sort of what this implies is that, we have a, if each pixel has its own phase error, and that phase error, requires, even 3 variables to describe, we now have 3 times as many unknown latent parameters as we do pixels in the scene. And, just, minor details, there's, well-established models for what this phase error should look like. Can be described as a sum of Zernike basis functions. And again, there are well-established models to sort of model the correlations between adjacent locations. The PSFs are going to, as you might imagine, change gradually over space. We also take advantage of a fast approximation of this forward model. So that, if we had the phase error at every single pixel in the scene, we'd now have to compute the Fourier transform to compute the point spread function at every point in the scene. And Mao et al. And Stanley Chan's group from Purdue developed a fast approximation that avoids these costly operations. But with this forward model in hand, we can now apply adversarial sensing to the turbulence removal problem. So we have the spatially varying blind deconvolution problem, where the Zernike coefficients associated with each pixel are the latent parameters. Classical methods alternating minimization or expectation maximization struggle. If there's as many latent parameters as there are pixels in the scene, there's just far too many to estimate or marginalize over. Feed-forward neural networks struggle because the latent parameter distribution is highly problem-specific, and it's challenging to generate paired data and train over all the levels of turbulence. Whereas adversarial sensing is well suited to this problem because it can adapt to the differential turbulence model at test time and can optionally use pre-trained generative models to impose priors. Adversarial sensing for imaging through turbulence looks, almost identical to what it did for cryo-EM. We have our physical model, physical process that produces the set of perturbed observations, blurry observations, and then we have our generator, which passes through a differential rendering engine. Here it's no longer tomographic measurements, but that fast approximation of the spatially varying blur I described earlier. We have our simulated measurements. We compare this distribution with this distribution and update the generator until it reconstructs the scene. When we are, say, reconstructing natural images or something, with which we have lots of training data, we can, optionally use, prior knowledge in the form of a pre-trained generative model here. For instance, we could, say, initialize a style GAN for face images. And so, for imaging through turbulence, without estimating individual PSFs, we can, ensure that the distribution of the measurements match the distribution of the predicted measurements. So we have, this is these true measurements. These you have some initial simulated measurements. The color's off. They don't match that well. And as you let this thing train over and over time, eventually it converges on a distribution of the predicted measurements, which is almost indistinguishable from that of the true measurements. And so by matching the distribution of the measurements, adversarial sensing successfully reconstructs the signal of interest. So shown here, we have, and in this case, we have an extremely strong prior in the form of the style GAN. That we can take a sequence of measurements that look like this and form a reconstruction that looks like this. Note also that everything's differentiable, and so if you need to say optimize the you don't know the turbulence strength at test time, you can just backpropagate that, make that a variable as well, and now sort of adjust, not even adjust your distribution of the forward model on the fly. Shown here we have initialize with we tell it the turbulence is too strong, initialize with tell it the turbulence is too weak. And if we let this thing adapt on the fly, it does just as well as if you told it this is what the turbulence is, given it that information. Somewhat surprisingly, it works well even if you don't have strong priors about the distribution of the images. We had the face images before where we had an incredibly powerful prior. but you can apply it to natural images as well, and you can also incorporate different priors about the distribution of the image in the form of different structure of the deep generative model. So you can use StyleGAN with a face prior, ImageNet with a natural image prior, or even just deep image prior using untrained neural network, using that as an implicit prior for the reconstruction. It works reasonably well, although not nearly as well as it does in simulation on real data as well. And just as Michael Unser mentioned, you can similarly extend this framework to handle reconstruct time-varying scenes. So in our case, the input, we have a deep image prior that gets latent, random latent initialization Z0. So in Michael's work, they fed in sort of a manifold of latents. So they had a they started off with Z0 and then gradually moved to Z final. Alternatively, you can just concatenate an additional channel, which has the timestamp. So timestamp of 0, timestamp of 1 over n, timestamp of 2 over n up to 1, and that allows you to reconstruct this scene from this sequence of measurements. Although you'll note there's quite a few motion artifacts. All right. So that was our approach to imaging through turbulence. You can also use this framework for apply this framework to nonlinear problems like Fourier ptychography. And we were particularly interested in long-range Fourier ptychography. So Ashok Veeraraghavan's group a few years back essentially took the same principles and techniques that Laura and others are applying to microscopic Fourier ptychography, and scaled it up to room scale scenes. And so you can imagine you have some laser source which is illuminating some far off scene, and then either you move the laser or move the position of the camera, and essentially capture a sequence of measurements at different orientations between the laser and the camera. This is accomplished with an LED and microscopy settings. The forward model here is that we're capturing a series of bandpass filtered images. So Michael went through this in detail. With these sequence of bandpass filtered images, you can set up a phase retrieval problem and essentially form a synthetic aperture to reconstruct a high resolution reconstruction of the scene. But whereas you have super precise control in microscopic applications, either you turned on that LED or that LED. In long-range imaging scenarios, it may be challenging to control the illumination, control the view angle. You might not have a cooperative illumination source. And so what we asked is what happens if if the view angles are unknown. Traditionally we assume here's the sequence of bandpass filtered images, and we know this is the pass band associated with each. What if we don't know this pass band? We're just given the sequence of images, and here again you can essentially plug and chug with the adversarial sensing framework, where you give it the sequence of observations where the unknown illumination angles, apply the differentiable rendering engine, get these two to match, and apply to experimental data from Ashok's group. We see that using this framework, we can successfully reconstruct far past the diffraction limit. So that's the bandpass filtered image, sort of the DC frequency, and then even without knowing the view angles, you can form the reconstruction. I should point out, here, as in the non-line of sight imaging case, the latent parameters are only two-dimensional. So we haven't compared to expectation maximization, and I'm not convinced that wouldn't work either. But in conclusion, adversarial sensing is sort of an interesting and unique approach to solving inverse problems with unknown forward models. It can handle unpaired measurements, and as we saw, can be extended to incorporate powerful priors in the form of degenerative models. So far, it's been applied to cryo-EM, imaging through turbulence, and sub-diffraction imaging. But there's a whole host of inverse problems with unknown forward models to which it could be applicable. And in closing, I'd like to acknowledge my students who did the vast majority of this work, Brandon and Mingyoung, as well as my collaborators at Stanford, Rice, Ohio State, SMU, Columbia, and Princeton, who did much of the other work, as well as funding from the Air Force. Great, thank you.